Welcome back to ECE 340. Today, homework number 3 is due, and that was full of convolution, or that was most of that assignment. Homework 4, please be looking for that. Hopefully that will be coming soon to a D2L box near you. Today, what I want to do is work through solving a circuit completely, getting the total response, not just the sinusoidal steady state, not just the transient, but all of those pieces combined. And we will look at that in a couple of different ways, one in the frequency domain and the other in the time domain. The frequency domain requires that we convert this circuit into its S-domain circuit equivalent, and that's going to then allow us to integrate or incorporate the initial conditions on our energy storage devices, and those will now become separate sources. Meaning if we had a one-input circuit and maybe we had an inductor, we could potentially have a couple of inputs driving that system, where one of the inputs is actually the initial condition on that inductor current. And that's what we hope to look at in today's lecture. If we have time, we will go through the time domain analysis and derive a state space representation for the same circuit, and then maybe even discuss how we could generate the approximate solution. How could we just turn the crank? How could we numerically drive that answer or that solution forward in time from a given initial condition and given input waveform? How can we simply propagate that result iteratively through to obtain the total solution or the complete solution in the time domain? Let's start with where I said we would go, which is incorporating initial conditions into the Laplace circuit analysis. And a lot of this material, here's now our S-domain circuit analysis discussion. And again, this is designed to give us the complete solution or the total solution. All transients and all forced behavior will be represented in the solution if we follow this procedure. If you forget how this might work, or if you don't have a certain textbook or a figure in your possession at the time, you can always remember Eli, right? Eli the Iceman, which allows us now to remember or recall the current voltage relationship for an inductor and a capacitor. With the inductor, or Eli, we know that the voltage or the electromotive force on that inductor is equal to L, the inductance, times the time rate of change of that inductor current. Similarly, with ice, we now have the capacitor's current equaling or proportional to, where the proportionality constant is the capacitance, the time rate of change of voltage across that capacitor. Those are now our governing differential relationships between voltage and current on our two energy storage devices, and with this we can now derive the results that are represented in figure 411, which is designed to allow us to immediately incorporate the initial conditions into our S-domain circuit model. Now, what we want to do, let's just look at this for one of these cases. Let's look at the inductor case, and you can then go through the derivation if you want for the capacitor on your own. I'm sure you're always looking for things to do after class or before class. This will give you something to do. Let's Laplace transform that governing differential equation. And let's go ahead and incorporate or keep track of the initial conditions. Meaning if we now have this relationship, what's the Laplace transform of that equation look like? We now Laplace transform the left-hand side. That's the easy part, right? That's just replacing a lowercase with an uppercase. So we just have to hit the shift key to do that Laplace transform, right? So this is now capital V sub L of S. That's now equal to L. That goes right through the Laplace transform. That's a constant times Laplace transform of a derivative. Do you remember what happens when you take the Laplace transform of a derivative? You multiply by S, and is there anything else happening? You have to account for the initial condition, don't you? And this actually is minus then I sub L of the inductor current at 0 minus. That's a really flat 0, so I'll try to, but that's a time domain value, I sub L of 0 minus. That's what the current was in the inductor at t equals 0 minus, and this is all based on this passive relationship between the inductor current and the inductor voltage. There, the inductor has a value of L. That's not L times I sub L of t. I hope that's clear. If it's not, maybe I can change this around and say this is now I sub L of t. The inductor's value then is L. But we can now play with this and create, this is the time domain version of our inductor. We want to create a frequency domain or an S domain version, and we can actually create this in two different ways. We can create one model that's maybe easier to play with if we were writing mesh analysis equations. So we're looking at series combinations on the right-hand side to create this voltage, and we get a voltage drop across two elements or terms. Or we could solve this for I sub L of S in terms of voltage, and now we get some parallel circuit that looks more like we would use that if we were doing nodal analysis. Let's start with the first one, which is the one that we probably all like to think initially of doing, and that's the series relationship. If I now distribute that L across, I have SL times I sub L of S, and if I didn't have any initial condition, there's my impedance relationship for that inductor. The impedance is now Z times I of the inductor, and Z is now SL. But I also need to have minus I sub L of 0 minus times L. That's now my total voltage drop across that inductor, which says in the S domain I have a piece of that voltage that's associated with the drop on that impedance, where the impedance is SL, and then I have another drop that's really just a voltage source, where that voltage source is now a polarity from minus to plus with a magnitude of L I sub L of 0 minus. This entire piece is the total voltage of that inductor, V sub L, and you could do a KVL around this and see that this voltage drop is equal to the right-hand side if we remember that our inductor current is flowing from left to right. Again, we're obeying this passive sign convention. The inductor current is coming into the positive terminal of that inductor's voltage. Now, if we have a circuit that has an inductor and we want to create the S-domain equivalent and we're wanting to do mesh analysis, we can replace the inductors everywhere with this series combination of an impedance and a source, where the polarity has to be observed, minus plus. This will then be useful if we were wanting to do the problem via mesh analysis. What if we wanted to actually do nodal analysis? Then what we can do is we can start with this same equation, but now let's isolate the current, I sub L, and just describe the relationship between the inductor current and the two terms that are left over. If we now solve this, V sub L of S equaling SL times I sub L of S minus L I sub L of 0 minus. If we now solve that for I sub L of S, we simply have 1 over SL, which is the impedance when it's multiplied by that voltage. So that's 1 over Z. And we now have that plus L I sub L on the other side, and we're dividing by SL, and so we end up with plus I sub L of 0 minus over S. What's the picture circuit-wise look like for this relationship between the inductor's current and the inductor's voltage? Okay, now you're drawing. Did everybody get that? Did everybody do their sketch of this? We have the current going in. That's the inductor's current, I sub L of S. But that's made up of two parts. One part is the conventional impedance piece, and the other part is actually a current source, and it's going in the same direction that the original current was going, and this has then a value of I sub L of 0 minus over S, and the voltage dropped is now between those nodes on the left and the right-hand side. And that's now for nodal analysis. Well, for nodal analysis, you might actually want to write this a little or sketch this a little differently. You might want to simply say, oh, let's kind of turn this on its side and say that we have now this I sub L coming in this way. Then we have something dropped across an inductor, and we have a current source due to the initial condition, which is now the initial condition in time over S, and here's our impedance SL, where the voltage drop is across those 2 points in our circuit. And now if we wanted to do mesh analysis, we could simply replace that inductor with this parallel combination of inductance or impedance SL and the source piece due to the initial condition. And this is what you would then use for nodal analysis. And that's really then half of the 4-part piece of figure 411. This is one of the 4 pieces, the nodal analysis piece when you're dealing with an inductor. We derived initially the series source piece that's associated with an inductor if we were doing mesh analysis. And we could have done the same thing with ice. And we may need ice in this room if it gets a little bit warmer, right? We've got some forced cooling a little bit with the fans, but we may need some more help in that regard. But you can then pull out, if you're getting hot, you can pull out figure 411 and look at the ice component, and that will then virtually cool you off. Correct? So you could do the similar development that we just did for the capacitor, and that will then be the ice piece. Let's look at an example of using this S-domain circuit analysis. Suppose somebody now has a circuit. Here's a resistor R sub 1. We have an inductor, let's say L sub 1. We have some voltage source, X sub 1 of T. We have a capacitor. Let's say that's C. Then we have another resistor. Let's call that one R sub 2. Suppose we have an inductor L sub 2 and we have a third resistor R sub 3. And maybe somebody says, oh, you know what, let's create some outputs. Let's say one output is Y sub 1, the current flowing through that inductor or flowing through R sub 3, and maybe Y sub 2 is this voltage drop across R sub 2. And now somebody, maybe your boss gives you this and he says, I need to know the time domain behavior in Y sub 1 and Y sub 2 for all time. What are you going to ask first? Are there any initial conditions? Do I need to worry about the initial energy stored in what? What could be storing energy in this circuit? RLs and Cs, right? Let's then say that he now says, okay, here's, let's say, I sub L sub 1. Here's V sub C. And here is I sub L sub 2. Now are you ready to go back to your desk and try to find this solution for Y sub 1 and Y sub 2 as a function of time? Probably going to need to know what X sub 1 of T is, right? The source. You need to know what the source is, but let's say now you're given that. You now are given X sub 1 as a function of time, let's say from T onwards. You're given I sub L sub 1 at 0 minus. You're given V sub C of 0 minus, and you're given I sub L sub 2 of 0 minus. Now, go back to your cubicle and work this problem, right? Are we assuming what? We're assuming this captures the essence of the circuit. So any losses that might be present have been absorbed into these representations for R sub 1, R sub 2, and R sub 3. Is this circuit or system stable? What do you already know? Well, you might also want to know what are the parameter values, right? You might want to know the R's, the L's, and the C's. But even before that, you could solve this in terms of variables, R1, R2, R3, L1, L2, and C. Variable parameters. Let's now analyze this in the frequency domain. Everybody likes to play with algebra, right? Instead of differential equations, Let's just solve this in the frequency domain, put this into the S domain equivalent circuit, and then we can find the answer if we inverse Laplace transform. Let's now analyze this circuit. In the frequency domain. What's a decision you might want to look at now? Or what kind of a decision or choice do you need to make? Mesh or nodal or combination, you probably want to be thinking, how am I going to solve this? And I see three panes there, or three, not pane as P-A-I-N. Maybe you're thinking that, but I was thinking more of a window pane. Isn't that spelled differently? P-A-N-E. So now we have mesh analysis. Maybe we'll do mesh analysis. If we now use mesh analysis, what do we do with our energy storage devices? What kinds of combination of sources are we looking for? Well, we just derived that. We don't want that, right? We're not going to put a parallel current source in with all the inductors, so we keep searching. That's what we want. Everywhere we have an inductor, we will combine the impedance of that inductor with a voltage source. With this polarity, incorporating the initial condition I sub L and the impedance or the inductance L. And we have to do the same thing for the capacitor. But we're now looking for series sources in figure, let's say 411, meaning we now have this inductor relationship. There's our inductor. Here's our voltage as a function of time, let's say. And there's our current as a function of time. Now we will replace that everywhere in the circuit. Whenever we have an inductor, we will replace that with an impedance, SL, in series with a source that has a source value that doesn't have any S's in it. It's just L times I sub L of 0 minus, where this drop is V sub L of S, if you need to know what that is, and the current is I sub L of S. Similarly, we're going to need to do the same thing for our capacitors. If we now have a capacitor, we're going to replace that with a series combination of its impedance. What's the capacitor impedance? 1 over SC. Is that clear that that's S and C are both downstairs? So let me not do it at an angle. Let's just say that. And now I have a source, but this one actually is different in structure. This is now the initial capacitor voltage, V sub C of 0 minus over S, and the drop is across both elements, and we have our current going through in series with those two elements. Anytime we have a capacitor, if we're doing mesh analysis, we will replace it with a series impedance series combination, or a source impedance series combination, where the source does now involve an S. In a sense, that sort of looks like a step function, doesn't it? Whereas with the inductor, that looks more like an impulse in the frequency domain. That's just a numerical value. Now we're ready to move on. Now we can start re-sketching that circuit in the S domain. We had a resistor on the right, or on the left. That comes through unaltered. We have an impedance. And we had this initial condition. The source is now minus plus left to right. L sub 1, I sub L sub 1 of 0 minus. Then we had our source. Which will have to be told what little x sub 1 of t was so that we could Laplace transform that, but now we have capital X sub 1 of s. We had a capacitor. Then we had another resistor. We had another inductor. And that's now what we have. Questions on that? Yes. What's the reason behind this polarity? It's all related to, didn't derive it, but you'll do that tonight when you go home. Remember what happened here when we did the the nodal analysis for the inductor? We ended up with a positive sign in this structure for our current. This is what you'll end up with equivalently when you start looking at the capacitor's impedance source relationship in terms of current. In terms of voltage for that capacitor. And that's where the polarity is different and you get that different structure. We didn't derive it, but that's where it would come from. Does that help answer your question? Meaning the polarities are different between the inductors and the capacitors source-wise, and that's where those are coming from just by re-deriving this Laplace transform of a derivative relationship and solving for the different currents and voltages in the inductor and capacitor. This is now what we have. And now how many sources do we have? We started with one input, but we needed to incorporate three initial conditions. And those three initial conditions now give rise to three more inputs. We now have a total of 4 inputs that are driving this circuit. 3 of those inputs are coming or resulting from initial conditions. Now we can write this relationship. Well, we said we were going to do it with mesh analysis, didn't we? Let's now write down our mesh equations. Let's say this is now I sub 1 of s. And for what I want to do, I want to write the relationships by inspection, and for that reason, I need to make all of my currents go in the same direction. And they're all going clockwise. I don't want to mix and match my directions of the currents in my process of deriving these relationships. Now I'm going to write the matrix relationships. I'm going to be expecting 3 equations, aren't I? I have 3 meshes, an I1, I2, and I3. I need to find an equation for each of those currents. If you simply wrote KVL around this first mesh, it would be R1 times I1 plus SL1 times I1 minus L sub 1, I sub L1 of 0 minus plus X sub 1 of S. That one's maybe, well, what did we have? We had I1 and it touched R1 and SL1, and those multiplied I sub 1 of S directly. What if we, what if we looked at this second mesh? Do the same thing, except when we came to R2, we would now have the drop from top to bottom voltage-wise as R2 times I2 minus I sub 3. Meaning the diagonal piece, or the impedance in that's multiplying I sub 2, is the sum of all the impedances that I sub 2 touches, and it touches R sub 2 and 1 over SC. And we'll sum those up. And that will be in the 2-2 entry of this impedance matrix. Also had I sub 3. Well, this current is touching a shared impedance, but it's going counter to how we're going, and that then is going to come into our impedance matrix with a negative sign. That's the idea behind these equations that I'm now going to write by inspection. Let me now talk my way through this. And I'll probably not give myself enough room, but how big is this left-hand matrix that I just wrote down but didn't fill anything in yet? It's going to be square, isn't it? We know it has 3 columns because we have the 3 unknowns, I1, I2, and I3. It's square, so it has to have 3 rows. That's now going to be forced by all of the inputs that drive these equations, and that will be on the right-hand side. Now we need to fill in these 3 rows on the left and the right. In the top row, that's going to be the row associated with mesh number 1. So we go back to mesh 1, and the first thing we do is we say, okay, which impedances are touched by I1? That's R1 and SL sub 1. That's it. Well, that's going to go in the entry, the diagonal entry of that impedance matrix as a sum. Meaning right now we have R sub 1 plus SL sub 1 right there. That's the 1, 1 location. And now we say, are there any impedances shared or touched by I1 and any of the other mesh currents? I1 does not share or touch an impedance that's also touched by any of the other mesh currents, which means that in the top row of this impedance matrix, I have nothing with I sub 2, and I have nothing scaling I sub 3. And I wrote that down essentially by inspection. Now I need to ask the following question. Do I have any sources in this mesh? I have 2, don't I? Now, I've identified the 2 sources. Now I need to ask the question, okay, here's a source and it's going to go on the right-hand side. Here's a source and it's going to go on the right-hand side. I need to know what's the sign of that source. S-I-G-N. The way to determine the sign by inspection is to say, if I increased this source, would it serve to enhance or make I sub 1 bigger? For the initial condition on the inductor, if I increase that, would that make I sub 1 bigger? It would make I sub 1 increase, wouldn't it? So this is going to come in with a positive sign on the right-hand side. Whereas if I increased x sub 1 of s in a positive manner, that's going to want to impede or reduce I sub 1. That source is going to come in with a negative sign on the right-hand side. And that's how I can quickly write down the right-hand terms. I now have a source due to the inductor's initial condition. That came in with a positive sign. And then I have the negative sign associated with the original input or source of my circuit. Any questions where those terms are coming from? How many columns do I have on the right-hand side? I just have one column. I have a lot of pieces in that column, but that's just one column. And I'm not going to pull out any of these, let's say, parameters. I'm just going to leave those in there. Can we now write the second equation? What's the process? I like to start with the diagonal piece, the 2-2 entry, since it's the second row. I ask what impedances are touched by I sub 2, and I sum those up. That's just R2 and 1 over SC, and that's going to go right here. So I have R2 plus 1 over SC. Does I1 share anything with I2 impedance-wise? No. Does I3 share an impedance or impedances with I sub 2? Yes, and since we're focusing now on I sub 2, and it's sharing I sub 3, that impedance is going to come in with a negative sign in that second row, meaning I now have this minus R sub 2. Questions on that? Do I have any sources associated with the second mesh? Now I need to figure out how do those come in on the right-hand side. Capital X sub 1 of S, if I increase that, is that going to enhance or impede I sub 2? I want to make I sub 2 bigger, isn't it? So X sub 1 is going to come in positively. What about the other source? If I increase that capacitor's voltage, initial condition-wise, what's going to happen? It's going to want to make I sub 2 smaller. That's going to come in with a negative sign. So I now have minus V sub C of 0 minus over S. Questions on the second row and where that came from by inspection. Third row. What do I like to start with? The diagonal piece, right? What impedances are touching I sub 3? I've got 3, don't I? And I just add them up. I now have R2 plus R sub 3 plus SL sub 2. Does I sub 3 share any impedances with I sub 1? No, so that 3-1 entry is 0. I sub 2 does share something, that's R sub 2. That comes in as minus R sub 2. And what about sources? I just have the 1, and is it going to be a positive or negative sign? It's going to be positive. So this is now L sub 2, I sub L sub 2 of 0 minus. If I don't have any dependent sources in my circuit, this is going to be a symmetric impedance matrix. And there it is symmetric, isn't it? The zeros, if I transpose that matrix, it would be the same. So it's symmetric. That's because I didn't have any dependent sources in that circuit. The only thing that we need to find is capital X sub 1 of S if they've already given us the initial conditions, and that's simply the Laplace transform of little x sub 1 of t. If somebody gives us that, then we're okay. Now what I didn't do in this S domain circuit is identify the outputs. What was Y sub 1? Y sub 1 was a current, wasn't it? And that was flowing through R sub 3. And I can do that same current here. I can now say Y sub 1 right there. And that's Y sub 1 of capital Y sub 1 of S. And Y sub 2, is that voltage drop. And if I wanted to find those, Y sub 1, we can't figure that one out later. Sorry. No one will know what I'm talking about listening to this recording, but you have the inside joke. Y sub 1 of S. We now want to write that in terms of our I's. Those are what we'll find. We can now inverse this impedance matrix, do the matrix inverse, and solve for I sub 1, I sub 2, and I sub 3. We now need to express Y sub 1 as a combination of sources and I's. It's pretty easy, isn't it? Y sub 1. That's just I sub 3. We'll get that automatically if we solve for the I's. What about Y sub 2? That's not much more difficult, is it? It's now the drop from top to bottom, and what's the way to find that drop from top to bottom? We just have to remember which current goes where, correct? It's going to be the net current going down in that resistor R sub 2. And the way we've defined our currents, we want down to be positive, and the one that's going down is I sub 2, the one that's going up is I sub 3. Y sub 2 is now the resistor R sub 2 times I sub 2 of S minus I sub 3 of S. In general terms, we have this impedance matrix, Z sub S. What's the size of that? That's a 3 by 3 matrix, but I can collapse all that down to just two variables, can I? Capital I is my vector of 3 currents, and that's equal to some source right-hand side I'll just label as V of S. If I wanted to solve this, I could find those currents, or at least their Laplace transforms, by pre-multiplying on the left. If we're doing matrix manipulation, we have to observe right and left, or the order with which we're doing this, because matrices don't necessarily commute. We're hitting things on the left. If we hit both sides of this equation on the left by Z inverse, then we isolate I, and we're left with Z inverse of S, V of S. Question? So am I reducing this whole circuit to one current and one voltage? Is that the question? So what am I doing here? I'm doing some magic? Hopefully not. So that's what I don't want to be doing. I'm simply trying to simplify my writing. My hand's getting sore. So I said this Z, I'm using that to represent this 3 by 3 matrix. Z, capital Z of S is now this 3 by 3 matrix. I can invert that matrix, and I'm going to then multiply that inverse of Z by this. This right-hand side is my capital V. It's a 3 by 1 vector of kind of a mess, isn't it? X sub 1 of S is going to be something, and these are going to be values or expressions. Does that answer your question on that? That's why I can't just say V divided by Z. I have to take the inverse of this Z because it's a matrix. It's a 3 by 3 matrix. If you want things in the time domain, you would just have to inverse Laplace transform 3 terms in this column vector of capital I of S. We have the 3 rows in capital I of S. We'll look at each of those and inverse Laplace transform, and that will give us little I sub 1, little I sub 2, and little I sub 3, and those are our mesh currents in our time domain circuit.
So is that kind of like doing the state space representation?
So is this like doing the state space in the frequency domain? Not quite. What we're doing is we're doing matrix representation in the frequency domain, but that's not quite the state space. But some of the pieces are going to be similar in terms of structure, but it's not really the same. Okay? We will end up with another way of solving this or looking at this in the time domain, and that's where I want to go next. Now, all we really did, if the matrix part confuses you, don't go there. Just stay here. Just stick with this. It's still, though, a matrix. If that messes you up, just write all the equations out. And just say, here's equation 1, and that's the top row. Here's my second mesh, and that's the second row. Here's my third equation, and that's the third row. Now you have 3 mesh equations. I was just trying to show you a new way to think about doing circuit analysis by inspection in the S domain. And then you can sort of just mechanically follow that process. Any other questions? So that is not really a state space. It's really just a matrix representation of the S domain circuit analysis. Questions? That now provides us with a solution in the back of the book, right? Now maybe somebody says, what can I check my work? One way to do that is to solve it a different way. And maybe your boss says, what's all this S stuff? Where'd you get all this inverse Laplace and Laplace? Just give me a solution. So now maybe what we want to do is play in the time domain. Maybe your boss says, can you give me the differential equations, the governing dynamics of this system? Let's now solve this circuit in the time domain. We have the same circuit. Let's not change that. And let's have our same outputs. We have y sub 1 and y sub 2. And now we want to write the governing dynamics or the equations of motion. How are these dynamics connected for this particular circuit? What kind of equation should we be looking for? And what I want to do actually is find a state space representation. And to do that, the first thing I need to do is find the governing dynamic equations and then put that into a state space form. I need to find my governing dynamic equations. But what I would like to suggest is you already can start to predict what you should be seeing or what you should be doing. And the first thing you might do is you might say, well, how many state equations do I expect to have? And how do you figure that out? Or how many state variables are you going to have? I thought I heard 3. I'm going to have this inductor current, aren't I? What are my, well, answered the question before I ask it. What kind of state variables should I be expecting in this circuit? Inductor currents and capacitor voltages. And I have 2 inductors and I have 1 capacitor. Let me call this state Q sub 1. And since I have another subscript on L, let me go ahead and call that Q sub 2. And then I'll call this one up here Q sub 3. I've now identified my 3 state variables. Q1 was the inductor current in L sub 1. Q sub 2 was the inductor current in L sub 2, and you could have defined those in different directions. That's okay. It'll be different from my state space, but it will be equivalent, meaning we'll get similar answers for Y1 and Y2. They may just look different in getting there. And Q sub 3, I decided to make that the capacitor voltage. And I labeled it, I think, from left to right, positive to negative. But again, that's not set in stone. You could have labeled that differently in terms of polarity. That's okay. You'll just get a different answer. But it will be an equivalent state space representation. Questions on the Q's? If we need dynamic equations, what are we looking for? If we're wanting a state space representation, what are we looking for? We need a Q1 dot or a Q1 prime. We need a Q2 dot or a Q2 prime, and we need a Q sub 3 dot. And those need to be written in terms of Q1, Q2, Q3, and X sub 1s, and X sub 2s if we have it. Questions on that? When we don't want any derivatives eventually on the right-hand side. We just want one derivative on the left. Our dynamic equations then that we're looking for we need a Q1 prime, we need a Q2 prime, and a Q sub 3 prime. And how are we going to find those? Well, sometimes you just kind of have to start and see what happens. But you can maybe be guided by the Eli and ICE. What do you know about Eli? V is equal to L di dt. So we can get a Q1 prime or a Q1 dot by looking at the voltage drop here. So maybe I would like to do a mesh here. Does everybody see that? And if I want a Q sub 3 prime, maybe there ICE is telling me I is equal to C dV dt. So now I might want to be looking at currents somewhere relative to Q sub 3. Because well, I'm getting ahead of myself. Let's just do a mesh around the left mesh. Whoops. Put an H where it should have been or an S where it should have been an H. Better quit trying to spell. What did I want to do? Let me go ahead and do KVL there. Is that okay? So let's do, and I'll just call that 1. So let's do KVL at mesh 1. And that's because of this notion that we're doing that. Eli is telling us V sub L is equal to L di sub L dt. KVL now tells us that if I start at the lower left-hand corner, I'm going to go up, and I'm going to have a voltage drop from bottom to top on that resistor of R sub 1, Q sub 1. Then I have a drop from left to right across that inductor as L sub 1, Q sub 1 prime. And then I simply go down across that source, and that I'm entering the positive terminal. I now have a plus X sub 1 of t. And I'm back where I started, and this now gives me an equation for Q sub 1 prime. If I isolate L1, Q1 and divide everything by L1, I will end up with Q1 prime of t is equal to minus R1 over L1 Q sub 1 of t plus 1 over L1, whoops, that should be a minus, shouldn't it? I need to put that on the other side, minus 1 over L sub 1 X sub 1 of t. This is now one of my 3 governing differential equations. Now what do I want to do? Maybe I need to look at the circuit again. That worked pretty quick, didn't it, on the left mesh? But now if I look at the right mesh, I don't have a current flowing through I sub or R sub 2, do I, in terms of my directly in terms of my state variables. I don't know what the drop is across R sub 2 in terms of my state variables directly or immediately, do I? So I can't really quickly write a KVL here. This current right now I haven't identified, have I? But if I looked at a super mesh, then I would have everything I need, right? If I simply now look at this super mesh, I can avoid the current associated with R sub 2. I don't have to worry about that since I don't have that in terms of my state variables. But I may need it. But for now, I can avoid it. So I'm now going to do a super mesh with number 2. So I'm going to avoid that middle mesh because of the current through R sub 2. So let me say the following. Let me say the middle mesh I'm going to avoid the R sub 2 current for now. And what I'm doing now is a super mesh at node 2. And if I start in the lower left corner, I'm now going minus x1, then what? plus q sub 3. That's a state variable. That one's almost too easy, that it's hard. But I now have minus sub 1 of t plus q sub 3 of t. Now I have the voltage dropped across that inductor, and that's from Eli. That's just L sub 2 times the derivative of q sub 2. And then I have the drop across R sub 3, but I have the current through R sub 3. That's just q sub 2. And that equals 0. This now allows me to solve for q sub 2 prime. And I typically like to write that with my q subscripts increasing. So let me start with minus R sub 3 over L sub 2, q sub 2 of t. That's that piece. Minus 1 over L sub 2, q sub 3 of t. That's this piece. Plus 1 over L sub 2, x sub 1 of t. And that's that piece. And now that's my second equation. Questions on that? What's left? I need one more equation, and I really need a q sub 3 prime equation, don't I? And I could find that by trying to find an equation that was associated with the current going from left to right. That would be C q sub 3 prime from ICE. If I'm interested in this current, maybe I want to find a KCL at that node. Just try to write KCL. Right there at A. And that's node A. Meaning I have I sub C of t. That's this current here. Then I have that's equal to I sub R sub 2 of t plus q sub 2, right? So I now have I sub C of t is equal to I sub R sub 2 of t plus q sub 2 of t. But I don't want to be writing this in terms of I sub C. I've kind of introduced a new variable that I don't want, but I can write that in terms of state variables. That's just C q sub 3 prime of t. And then I have I sub R sub 2 of t plus q sub 2 of t. So I'm going to have to get rid of this guy in terms of x sub 1, q1, q2, or q3. So if I now come back here, well, let me just introduce some more notation. If I'm introducing notation, if I call this V sub R sub 2, then I sub R sub 2. So here's some observations. V sub R, whoops. I sub r sub 2 of t is just v sub r sub 2 of t over r sub 2. By definition of the way I created v sub r sub 2 of t. But now can I find v sub r sub 2 in terms of state variables and inputs? Now if I look at this mesh here, I have a KVL saying minus x1 plus q sub 3 plus v sub r sub 2, and there I can now solve for v sub r sub 2 in terms of x1 and q sub 3. The mesh, the middle mesh is now coming back to help me. Does everybody see that? That's a pretty busy circuit. That's almost a piece of art, isn't it? All that labeling. You should see beauty in that, right? Especially with all the colors. This is just a palette of colors. 4-color circuit. What do we have? I just did a KVL at middle mesh, which said minus x sub 1 of t plus q sub 3 of t plus v sub r sub 2 of t is equal to 0. This now can be solved for v sub r sub 2 of t, and that's simply equal to x sub 1 of t minus q sub 3 of t. That can now be placed up here, and that I sub r sub 2 can be placed right there. Can we put all of those pieces together? We had the current through the capacitor, which was C q sub 3 prime, and that was equal to the current through I sub r sub, or through r sub 2, which is now x sub 1 of t minus q sub 3 of t over r sub 2, and plus q sub 2 of t. Is that okay? And now divide everything by c, and I have q sub 3 prime is equal to 1 over c q sub 2 of t minus 1 over r sub 2 c q sub 3 of t plus 1 over r sub 2 c x sub 1 of t. Questions on those three equations? Now can you put those in a state space form? What are my outputs? Those you should be able to build the matrix. What's your A matrix? What's the size of the A matrix? Because now I'm saying we have, and again I'm going to collapse this down into something that looks, and this is actually just one input, isn't it? What are the dimensions on A? It's 3 by 3, isn't it? That's your system matrix, and that's square. What are the dimensions on B? And you should be able to build these up and isolate that. How many rows are in B? Well, it has to have the same number of rows as A, doesn't it? And how many inputs did I have? Just one. So there's our B. What's Y1 of T? In terms of states and inputs, what's Y sub 1? That's just Q sub 2, isn't it? What about y sub 2 of t? That was just this beast, wasn't it? V sub r sub 2. And we just found that to be x1 minus q sub 3. Y sub 2 is then minus q sub 3 of t plus x sub 1 of t. What are my D matrices? So if there's my output, how big is here's Q1, Q2, Q3. And then I have a direct feed-through term. And luckily I have an infinitely wide piece of paper. What's the size of C? It has the number of rows corresponding to my two outputs. So it has 2 rows, doesn't it? And how many columns? Well, it has exactly the same columns as the length of my state vector, which was 3. C is then 2 by 3. And wasn't the first row simply Q sub 2? And how big is my D matrix? How many rows does it have? It has to be compatible with the Y's, and I only had 2 Y's. How many inputs did I have? 1. So it's a 2 by 1 vector. It's in the bottom row of this y sub 2 expression. Is that okay? Here's my C matrix. Here's my D matrix. Now we have an A, a B, a C, and a D. We can put this in MATLAB and go to town. You can give your boss as much as you want now. We just have to specify the initial condition and x sub 1 of t. I know you want to read ahead. Chapter 10, Section 3, you can find a solution to this. You can also see this, maybe you remember it from your background chapter, B6. Bingo. Oh no, that we were playing Battleship, weren't we? So, do you have something at B6? Your interceptor or whatever your carrier. Do you want to see a numerical solution to this so that you could basically put this in Excel into a spreadsheet and number crunch the solutions? Then you could simply iteratively figure out what's going to be the next value of your state at a particular time step. Now, before we do that, what would we need to know? Right now, we don't have any R's and C's, do we? We need to know what the parameter values are if we're going to simulate this. But once we have that, then what's the next question? If I give you the initial conditions, and that's going to be I sub L sub 1 of 0 minus, I sub L sub 2 of 0 minus, and V sub C of 0 minus, and x sub 1 of t. And if I give you all the R's, all the L's and the C's, now you can go to town, right? But once you have these R's and L's and C's, what do you need to know if you're going to start looking at this in MATLAB? You're probably going to need to know the poles. The poles influence the natural behavior of your system. You also want to know what's the structure of x sub 1 of t. Once you have the structure of x sub 1 of t and these r's, l's, and c's, you can get the poles by finding the eigenvalues of your A matrix. And maybe we'll talk about that. What's today? Tuesday? Wow. Thursday. I'll see you then. Don't forget your homework.